Alright, y'all, welcome back. This is another piece of the Teardown series that I wanted to get into with the IBM server. This one I should have actually launched with, because this is probably one of the most important pieces of all. This one here takes the AC voltage from the utility and turns it into a DC voltage that the server is going to use. This is called the AC-DC converter. And this is usually this is the first step for power conditioning. It's massive. It is, again, it's for a 19-inch rack, it's 17 and a half. How deep is this? 16 and a half inches deep, about 2.5 inches tall. And it's very heavy. This is 13 kilograms, 30-some pounds. So, yeah, this is actually one of four, I think, 4 or 6 the computer had. I think there was 6 of these. I'm not sure. Depends on how much power they plan on using. It has an input connector on the front, which is, I believe, is for battery. It goes up to the battery bank, and we'll talk a little bit more about that. But again, it locks in. There is a power switch on the beginning here on the front. Unlock off, lock on, and when you turn it on, oh man, try it. Yeah, see what I mean? And when you turn it on, it locks. This tank comes out and it locks it in the rack, so you can't pull the assembly out while it's powered on. That would be catastrophic for the connectors at the back. You would have it would not be pretty. So let's have a look at this. On the front, there's a power switch and an input connector for power. It says IBF power, but I believe this is for the battery bank. And that's about it. On the back, oh my god, there's 2 connectors. This one here will be 3-phase AC input. This one here will be your plus 350 volts output. And then we have some data control lines here on the end. Ventilation's all cross flow. The sides are punched out for full ventilation, both sides. And this sat in a rack, and I believe it held 4. It was capable of holding 4 of these components, and there was a big massive fan on one side, and it would blow air across. So let's look at this. Let's have a look at the label here. Let's reposition the camera. Alright, so again, we have made in Slovakia by Delta Energy Systems of Germany, and it's made in Slovakia for IBM Corporation. This component here takes in 2 single-phase or 3-phase 50-60 hertz, and it can take 200 to 240 volts at 45.5 amps. It can take 380 to 415 volts at 23 amps. And it can take 480 volts at 18.5 amps. That's your input power. It's flexible enough to know which is being fed. It has a input battery of 360 volts DC at 15 amps max. That would be the backup power. And it provides an output charge current of about 250 milliamps at 405 volts. On the output side of things, we have a 350 volt line, and that produces 22.9 amps maximum. And then there's a 6 volt and 12 volt, I'm assuming just for internal logic and control circuits. So let's open this up and have a good look inside. Alright, so take the lid off. I had to drill out one of the screws because it was seized in place. This is aluminum lid. It's quite thick too. It's like 2 millimeters. So Pull this off. Insulating sheet. Typical insulating sheet. Get rid of this. Alright. We got a lot going on here, so let's take a look. So this is the three-phase input, and these are 30 amp fuses. A, B, and C phase. Everything's pretty typical for a power supply. It's got the common mode chokes, the capacitors, but this is obviously on a bigger scale. You got these huge chokes, and I believe that's 12 gauge wire. This is 14 gauge, 12 gauge, so we're common mode chokes. Check out these capacitors here. Look at this thing. 3.75 microfarads at 850 volts DC. Look at the size of that thing. It's massive. So all of this here on this one side is all power conditioning and filtration. Not much else to say about it. It'd be like just like your typical PC power supply, but it's scaled up on a grand scale here because we're dealing with 450 some volts, three phase, and we're dealing with a lot of current and a lot of power going through. So pretty interesting, I think. Anyway. And then it continues on. Got a bank of capacitors here. 450 volts. These are 620 microfarads at 450 volts, and we got 2, 4, 6, 8 of them. So there's your bank of capacitors on the input. This side here looks like we got some chokes here, and they look like they're wound with foil. We'll take one of these apart here. Let's look at this controller first. There's a lot going on here. So we got some serious opto-isolation here. These are opto-isolators. It looks like, because there's slots cut in the circuit board to provide voltage isolation. I don't see a controller here, but this is probably just the watchdog circuit that's keeping an eye on things. There is a crystal oscillator here, so this might be a controller, but it doesn't look like it's very powerful. And there's a crystal oscillator here as well. Let's pull off these heat sinks and see what we got going inside here. Alright, so we got the screws out of the heat sink. Let's pull this off. You can see it's about an inch tall. Fully coated with heat sink compound. Insulated on this one end. It's a fairly robust heat sink. It weighs probably 4 or 5 pounds alone. But it's a nice chunk of aluminum. And you notice that the orientation of the fins is cross ventilation for the fans. So get rid of this. And underneath, I believe this here is our bridge rectifier. And here we have banks of transistors. And we've got, you can see right here, Q24, left H bridge, Q26. This is the right H bridge, Q28, Q27, CR21, CR23, CR22, CR20, Q3, source drain gate, that's a MOSFET. And I believe these other ones are insulated gate bipolar transistors. This one here is marked CR3. This is called Buck 1 and Buck 2. Boost, and buck. So they're doing some trickery here with the transistors. Not sure exactly what's going on, but I don't know if these can come off just yet. Each one has a individual temperature sensor embedded into the aluminum to monitor the temperature of the heatsink. Let's see if we can pull this off. I don't want to break anything. No, I think they're soldered in there. I might have to get the soldering gun out to get one of these out. But let's have a look at this. So we got our input power fuses. I'm surprised that they parallel two 30 amp fuses to make 60 amps. I didn't know that was acceptable to do that with fusing. You could parallel them up, but they're doing it here. So we got 3 input fuses, some Y2, X2 rated caps on the input, chokes, more caps, metal oxide. There's 4 of them here, 5 of them. Goes into the 3-phase bridge rectifier, then it goes into the capacitor bank. And from there, I don't know what they do with it. They have these circuits here that obviously boost buck the voltage. Doesn't look like there's any isolation here from the mains. Let's pull this board out of the chassis. Alright, so I got the screws out. We can lift this board out. It's quite heavy. A lot of weight here. I'm just going to get rid of this on the bottom. Of course, we got an insulating sheet again. Installed steel bottom. Let's have a look at this. This is interesting in itself. So I removed one of these capacitors just to have a look at it. They're quite massive for a 3.75 microfarad. 850 volts. I can only imagine this is a film capacitor, and I can imagine the thickness of the film that they needed to put in this to get 850 volts insulation on that. It'd be quite thick, and it's not very heavy. It's fairly light. It's as the voltage goes up, you need to increase your dielectric strength, and that is, you know, proportional to the thickness of your film. And the metal foil would be the same if it was a lower voltage cap. There's no change there. It's just the thickness of the insulating film that needs to grow thicker as the voltage climbs. Kind of interesting. This is it's not very often you see a capacitor like this, high voltage cap. This is your 3-phase to DC bridge rectifier, and it has on the input it's got your 3 phases, and it's all potted with epoxy and bonded to this heatsink. I believe this might be copper. Let's take a little scratch at it and see. Copper is your best. Yeah, it's copper. Copper is your best conductor of heat, aside from silver, and you know, it's much better than aluminum. But this thing here, this bridge rectifier alone handles 50 amps, and according to the part number, this is a 1600 volt bridge diode. So it can handle up to 1600 volts at 50 amps. It's quite a substantial bit of power can flow this to this tiny little bridge, and it better be heat sinked properly or else it's not going to survive, I'll tell you. Alright, so here's one of the blocks desoldered, and this one in particular has 3 transistors and 4 rectifiers. It's on a solid block of aluminum. Let's take this tape off and let's pull one of these apart. Where's my screwdriver? Again, what we got is a plate of copper, and on that plate of copper we have the devices are mounted. And I believe they're soldered down. Like, that way they're going to get the maximum heat transfer. I don't think any adhesive would stand up to the thermal cycling and you know, the abuse of. So again, we get a copper plate, and these devices are, I believe they're soldered down. I don't see. Let's try bending this. I can get one of these to pop off. Yeah, they're just soldered on. So essentially what they're doing is they're bringing in the 3-phase power, filtering it, rectifying it into DC, using a capacitor bank as your storage, and they're using it on these 3 devices here. Well, they're not really devices, they're just community heat sinking. This is called Buck 2 here, there's a pair of transistors. And this is called Buck 1, there's another pair of transistors. These are insulated gate bipolar transistors. And then on this one, they have a boost pair of transistors here. And I don't see a second pair of boost. But they have an H-bridge configuration. This here, these 2 transistors here is your left H-bridge. These 2 transistors here are your right H-bridge. And then you have a bank of rectifiers. So we can kind of see the progression here. Once the power comes in, it's conditioned, it's filtered, it's rectified into DC. Got a storage bank, capacitors here, and then using these H-bridge and the buck boost, they are producing a 350 volt DC output, and that comes out here, I believe. Let me see. Yes, it comes out here, and it's cleaned up with this choke, these chokes, and then it's filtered, and then we have a filtering of 450 volt, 220 microfarad before it hits the output. And that's basically all there is. And then the rest of it is monitoring and control. There's a small switch mode power supply here, and it's got a relay, and I'm assuming this power supply powers this board that was sitting here. This board provides isolation and communication back to the host flexible service processor, and that would be through those data pins there. As far as parts scavenging goes, this thing looks like a gold mine. How often do you find these caps, 450 volts at 620 microfarads? And these chokes, these are wrapped with foil, they're not wrapped with copper wire. Foil wrapped chokes, very high current, very costly to make. Let me pull this one out, we'll have a look at that. So here's a look at one of the inductors on the output. I believe this is on the output because yeah, it is. I'm pretty sure it is. From here through, like I said, it's wrapped with foil, not copper wire. It's got 4 leads. I think this is a common mode choke, the way it's wired up here. It has feed through from one coil to the other, so maybe it's not a common mode choke. Maybe it's just it's not a transformer, but it's definitely a choke. It even has a Delta part number on it, MP155D, and I imagine they rolled their own on this one. I don't know if you could buy something like this. You'd have to special order this, and it'd probably be just easier for them to roll their own. And let's open this up a little bit and see inside. I don't know if I can. It's all, you know, it's silicone together. But yeah, it's wrapped with copper foil. Fairly substantial copper foil too. It's not very thin. But it's probably carrying, I don't know how many amps this thing would carry. Quite a few. I'm sure it would have quite a low resistance. So as far as harvesting parts off this thing's like a gold mine. You know, it's just loaded with stuff that you could pull off and use. I don't know if you have a use for these monster caps or these monster inductors, but the copper salvage out of this would be good. Got a bridge rectifier here with a heat sink and power resistors. What do we got for resistors here? Can't read them. 5K, I think. Capacitors. Gold mine for capacitors as well. So I'll be harvesting a lot of parts off this before I scrap it. I really don't have use for these inductors, but I'll recover the copper out of these. But yeah, that's a good look at one of the input power conditioners, power converters. Lots of interesting stuff in here. The semiconductors I'll probably harvest. You know, there's a few relays. There's some of these smaller caps I'm not worried about. But the odd caps, like these big high power, high capacity, high voltage caps, those are always good to keep them. Keep a few on stock. There's 450 volts, 56 microfarad, 450 volts, 220 microfarad. So these are good for you know, replacing in computer power supplies. These are high quality caps. Nippon Chemicon. The aluminum I'll harvest and recycle and get paid for that. A lot of these caps, I really don't have a use for these 850 volt caps unless I dream something up. Maybe I'll be able to make a project or something. But yeah, it's a gold mine, this one.